Hi, my name is Steven Sims. I'm a certified instructor for the SANS Institute and course author for the course Security 709, Developing Exploits for Penetration Testers and Security Researchers. In this video, I'm going to demonstrate a method to brute force address space layout randomization with a vulnerable program. It's a question that comes up a lot as to how effective ASLR truly is on an operating system, and it varies greatly. It depends on the amount of randomization that the operating system can take advantage of. The more bits in the entropy pool, the higher the randomization, and the more difficult it is to defeat it. Commonly, something like a stack overflow is relatively simple in theory, depending on the number of OS controls that have been implemented. For ASLR, which is what we're going to focus on today, again, it depends on the number of bits in the entropy pool. So on this particular system, as I'll demonstrate soon or shortly, is going to be 20 bits of randomization on the stack. So that's just over 1 million potential addresses as to where a particular variable that we're interested in memory could be located. So with this one, I'm going to first show the vulnerable program, and then we're going to exploit the vulnerable program without address space layout randomization, just so we can understand the simple POC program. Once that's done, we'll go ahead and turn on ASLR, so you'll be able to see what exactly we're up against and how our exploit fails. We'll then quickly write a little C program and put it into a for loop and see how long it takes us to actually brute force the vulnerability with ASLR fully enabled. This is a Kubuntu image running kernel, I believe it's 2.6.23. Not much has changed since then, unless of course you are adding things like the PAX patch and other more strict controls. So without further ado, let's take a look at the program. Again, it's a simple vulnerable proof of concept program, and we'll just run it and enter in an argument. Just say hello, and as you can see, it simply says hi there, and it gives you back what you typed in. If we make it a little bit longer, add a bunch of A's on the end, you can see that it goes ahead and truncates the output to a certain number of characters. So one thing we want to try doing, just to see if there's a buffer overflow in it here, is using a scripting language such as Python is what I'll use. So let's say Python -c print A times, let's say, 1,000. And as you can see, it comes up with a segmentation fault. Again, as I mentioned, it's a simple stack overflow, but our focus is on ASLR. So let's load this up in the debugger. So we'll use GDB, the GNU debugger, and take a look at the program. This has not been stripped, so the symbols are available. There's only one function in here. Again, simple program. Copy function. This is the only internal function that's listed, as it's not calling from the procedure linkage table, such as that with exit and other ones. So let's go ahead and disassemble the copy function and see what's in there. Again, very simple function. You can see one called a stir copy down here, which is likely where the vulnerability is located. Up here you see an assembly instruction saying LEA, which is load effective address, and it's giving you a 2's complement value. So what we need to do is take this and convert it over into a positive integer. That way we can figure out exactly how large the buffer is for this particular program. So we can jump over and use Python or anything else that you want to use. We'll say import struct, and then we're going to say temp equals struct dot unpack, and we're going to take a look at what this value is going to give us. Give me 1 second here. And our value was 0D-A8. So now we've assigned that. We can say print 4096 minus temp, which gives us 600. So the buffer size is actually 600. So if we jump back over here, we should be able to say Python -c, actually we say run first, Python -c print A times, let's do 604. What 604 should do is it should cause a segmentation fault, because we'll overwrite the saved frame pointer, but we won't be overwriting the return pointer at this point. So we run that, and we did get a segmentation fault, as you can see in frame dummy. So let's go ahead and change that to 608, and we should see 41414141, which of course is the ASCII equivalent to A. and we get what we expected. So we cause a segmentation fault, which of course means that the instruction pointer tried to execute something at this memory address, which is an invalid memory address. So at this point, we can continue on with our very simple exploit before we go ahead and implement ASLR. If we take a look at the stack at this point when it crashes, we should be able to see what we're up against. So we can go ahead and examine memory. If we do actually -4, we should be able to see our return pointer overwrite, and that's where the return pointer was. So ESP, the stack pointer, is currently pointing right here. So what we want to do is, since we're just trying to be simple here, we're not worried about being messy, we'll throw in a quick NOP sled here, and we're going to use an address inside that NOP sled to be able to return to and follow that up with our shellcode. So again, very simple exploit. So let's go ahead back over to here. We'll say 604 A's, and we're going to say plus BBBB, so we should be able to see 42424242. It's where the segmentation fault occurs. Plus, and we'll put a NOP sled of 100 bytes in here for now. And we need to follow that up with our shellcode, but we don't have our shellcode yet. So let's go ahead and send this in. And we get what we expected, 42424242. Now let's take a look at the stack. And we see our return pointer guess, which is right here, followed by our NOP sled. So what we're going to do is just use an address such as this one right here. And we're going to return to this. So we're going to overwrite the return pointer with this address on the stack, which should land us in our NOP sled, which of course is a non-operation instruction. It does nothing. It just slides down until it's going to hit our shellcode. So we need to get our shellcode, and we need to use this address as our return pointer. So I'm going to drop out of GDB, and we're going to say, I've got the shellcode in here somewhere. That's the shellcode that we're going to use. This shellcode is simply going to restore us back to root, and with the function setReuid, and it's also going to run execve with /bin/shell. So if we're successful, it should spawn a root shell. This program, of course, I didn't show you, but it's running with suid of root. So right now we're logged in as a regular user. We don't have a hash or a root prompt. That's what we want to get. So let's go ahead and say, set up the program, and then we're going to use Python, of course. A times 604, which takes us to the return pointer. Plus, now in little endian format, we need to put in our return pointer guess, which of course is this address that we discussed up here. So I'm going to put that in reverse order. So /x BC, /x F4, /x FF, /x BF. There's our return pointer, plus our NOP sled. So /x 90 times 100, plus now finally our shellcode. So we close that out. So if we hit enter and everything worked out the way we want, we should get a root shell prompt on a screen, and we do. So that's simply we are able to take advantage of that vulnerability. And we can say, who am I? And of course, we're root. So let's exit out of here. The next thing we're going to do, actually real quickly, I'll show you this simple little program. All this program does is it moves the stack pointer address into EAX and prints it out to the screen for us. And we'll just run that guy. And you can see that the stack pointer is always at the same location, which shows us that ASLR is not enabled. So let's go up and enable ASLR real quickly. And we can do that by echoing 1 into /proc/sys/kernel/randomized VA space. 2 may also be a valid option. Drop out of here. We're back to a root or a command shell at a user level. We run the ESP program again. Now notice how the address here keeps changing. It's not static like it was above. And actually, these bytes here are the ones that are being randomized. The others stay pretty static. So the first byte is static. That's for segmentation purposes. It can't randomize all 32 bits. The second and third bytes and the next nibble are all being randomized. So that's 2 to the 20th. The last nibble here on the end is always at the same address or value. So we've got 2 to the 20th. Again, just over 1 million possible addresses. If we simply bring up our exploit again and try to run it now, we get segmentation fault and it fails. It's failing because our NOP sled and our shellcode is not at the same location each run. So it's within that 2 to the 20th range or somewhere close to that.